Hello, Math 125 students. Welcome to the lesson about exponential functions. Okay, everyone. So far, we have seen functions like y equals x squared, y equals x cubed, square root of x, cube root of x, 1 over x squared, absolute value of x, and so on. We actually studied quite a lot in Module 1, where we also studied the transformations of x squared, x cubed, and so on. So we studied transformations of these functions so far, which is very nice. This time, I'm going to teach you the new functions called exponential function and logarithmic functions. Okay, first, we learn exponential functions, and it looks like this. Okay, in this lesson, we are going to study functions of the form y equals, and this kind of function is called an exponential function. Did you notice the difference between the functions that we have seen before and then our new function, which is the exponential function? Did you notice the difference? Please remember that the difference between the previous ones and this one is that our new function has x as an exponent. Remember, our new function has x at the top, which is a power. But all the x's in the previous functions are located underneath the exponent, which means x squared, x cubed, x to the power 1/2, and so on. Okay, that's the clear difference between the previous examples and then our current one. Okay, if you are ready, let's write it down. This is what we have just said. X as an exponent means exponential function. Did you see the variable b? This b is called the base of the exponential function. You know something? This b controls whether we have a growth exponentially growing function or exponentially decaying function. Look at the difference. I have two x and y axis, and the first one, I'm gonna sketch exponential growth function. Exponential growth function happens whenever the base is more bigger than 1. So suppose everyone, I have y equal to 2 to the x, y equal to 3 to the x, and so on. Then the graph looks like this. On the other hand, if the base is a like fraction, say b is 1/2, if you have taken chemistry class before, if you talk about half-life of a substance, then this b must be 1/2 or 1/3 or 0.5. If it's less than 1, then it's the shape of the exponential function looks like this. It's decaying. Okay. The first one is growth, and then the second one is decaying function. So let's write it down on your paper. Okay, everyone. As a warm-up, I have opened the textbook questions on the left-hand side screen. So it is in section 4.1. As a warm-up, I would like to go over number 14, number 15, number 16, and 17 together. The question is pretty simple. Just by looking at the function, determine whether each equation represents exponential growth, exponential decay, or neither. Well, look at number 14. 300 times 1 minus, it's like x, okay? 1 minus x to the power of 5. Isn't this look like somewhere here or here? So this is an example of a polynomial function, not the exponential function. So The answer to number 14 is neither. Number 15. It looks like we have a times b to the power of x, like this. 220 here, and then the b is 1.06, and we have x. Did you notice that? 1.06 is more than 1, which means exponential growth function we have here. Could you please look at the bottom one, number 17? We have 0.97. That means it's exponential decay function. Lastly, this one is neither because it looks like a times b to the power of something, right? But it must be x, not 1 over x. So this is not growth or nor decay function. In the second part of today's lesson, I want to teach you how to sketch transformed exponential function. For example, if a is greater than 1, you know from module 1, it is vertically expanded by a factor of a. If x has a horizontal shift, then it looks like x minus c, and then if it has a vertical shift, plus d. So we're gonna play with the transformations of sketching exponential functions. However, for the rest of the lesson in part 1 here, I want to teach you one good real life problem. Real life problem involving exponential functions is a money problem. Look at the formula. The title is Compounding Interest, Money Problem. This is fundamental to everyday banking. If you invest some money into an account, the interest accumulates, and at the end, you get more money. So, we're going to study this right now. Stay tuned. The key formula for compounding interest money problem formula is um, looks like this. This A represents the final amount after t years, time t. And this P represents the initial amount. And this R represents the annual interest rate. And here we have both n at the denominator and n at the exponent. This n represents the number of compounding periods. What does it mean, everyone? In order to find out the n, you just have to look for the following words. Look at my table here. Whenever you see compounded annually within a question, right away think about n. The number of compounding period is 1. Whenever you see semi-annually, compounded semi-annually, then n equal to 2. Compounded quarterly means n is equal to 4. Compounded monthly means n equal to 12. Compounded weekly, how many weeks do we have in a year? There are 52 weeks in a year, so n must be 52. Daily, everyone knows this answer. Compounded daily means n must be equal to 365. This is the summary of all the n values depends on compounding period. Okay, if you understood everything so far, let's start the first example on using this formula. Here's the question. The question is, suppose you went to the bank and then deposited $3,000 in your account, which pays 3.12% interest compounded monthly. Here's the question. Find your final amount after 2 years using this formula. So we know the initial deposit is 3,000. We know the annual interest rate is 3.12%. That means, be careful, 3.12% as in decimal number, it is 0.0312. So you have to put that 0.0312 here, and then compounded monthly means n must be equal to 12. That's compounded monthly. So altogether, just plug in numbers and get the answer. By the way, um, we're looking for the balance after 2 years. That means the time that we have to plug it in here is 2. Could you please punch this on your calculator and check that my work is correct? I got this. I've got the final amount of $3,191.91. So the accumulated interest was $192.91 after 2 years. Okay, that's the end of this first example. Okay, the last formula that I would like to tell you is this. The depreciation, in other words, if you purchase a car, after 1 year, the, the value of your car drops drastically. And then after another year, the value of your car drops gradually, and so on. So this kind of formula tells you the final amount of your car's value after how many years? This much of years, with R being the depreciation rate. Try to listen to the video, watch the video, and write down everything what's in there as much as you can and submit it on Canvas. Calculate the initial deposit of an account that is worth this much amount after earning 5.5% interest compounded monthly for 5 years. So right away, you write down the formula A equals P 1 plus R over N and T. This is the formula we have. And then we know that this is the final amount. And then we are looking for the initial amount. And we don't know what that is yet. Here we have 5.5% annual interest rate. This means our R has to be 0.055. Compounded monthly, that means N is equal to 12, and then T is equal to 5. So we know all the pieces of information that we know and plug it in like this. Now, you know we're solving for one particular unknown variable, which is P. To solve for the P, we divide both sides by this whole expression. Using your calculator, but we need to answer this round to the nearest dollar. In other words, the answer is congratulations. That's the end of this example. Part number 2. We are going to see more real-life problems, such as depreciation rate problem or population rate problem. For the depreciation problem here, the formula is A equals the initial amount times by 1 minus to the power of t. And this R is the decay rate for this depreciation process. For the population problem here, we usually write P to be the final amount, and then the initial amount is P0 times by to the power of RT. We're going to study more about this near the end of this part of the video. Okay, let's first study the easy one, which is depreciation rate problem. Here's the example. A new ATV cost $800 at the beginning. At the beginning means P is equal to 800, and then the value of ATV decreases by 10%. Be careful, this is the depreciation rate, so this must be the R, which is 0.1 as a decimal number. Part A, write an exponential decay model for this ATV after t years. So the formula is A. Now we know the principal amount, which is $800. And we also know the depreciation rate, which is So everyone, this is the model that describes this exponential decay situation. Part B, estimate the value after 5 years. This is piece of cake. You just have to plug this 5 into the t and use your calculator to get the answer. This is approximately equal to $472.39. Thank you very much. That's the end of this part 2. Okay, welcome back everyone. In this second part of today's lesson, I'm going to sketch exponential functions. Do you remember in module 1-2, we tried to use ABCDE method. This time, you can do the same way, or you can accept my new way of doing this. Okay, first of all, I'm gonna find A, B, C, D, E for 2 to the x graph here. Okay, let's begin. Okay, now I'm ready to teach you how to sketch very first exponential function for our course. Y equals 2 to the x. I'm gonna plug it in. Let's say I'm gonna plug it in 0 first. Anything to power 0 is 1. It's not 0. So we have order pair 0, 1 on the graph here so far. Now, if you put 1 into the x, you get 2 to the power of 1, which is 2. If you plug 2 into the x, you get 2 to the power of 2, which is 4. If you plug negative 1 into the x, you get 2 to the power of negative 1. Let me explain in detail. 2 to the power of negative 1, if you believe me, it's 1/2. Using exponent law, this is equal to this, okay? 1/2 is same as 0.5. Or you can just treat it as a 1/2. It doesn't matter. Now, if you think about negative 2, imagine you have 2 to the power of negative 2, which is equal to 1 over 4. 1 over 4 as a decimal number is 0.25. Okay, once you're ready, let's plot these points on the graph here. We have negative 2, 0.25. We have negative 1, 1/2. We have 1, 2. We have 2, 4. And then the graph of this exponential function looks like it's growing, right? It's growing. Congratulations on graphing very first exponential function in our course. You clearly know that this is a growth function because our base 2 is more than 1. And here's very important for you to remember for sketching exponential functions. There's always horizontal asymptote. The horizontal asymptote is located at y equal to 0. Please remember this. Okay, as a summary, the asymptote is happening at y equal to 0. The center for this graph is, did you see? We have 1, 2, 3, 4, 5. The point right in the middle is the called center, which is located at 0, 1. This center is very important, everyone. For now, just know how to find center, okay? To find out the center, think about the x-coordinate. Which x makes the whole exponent 0? Obviously, x equal to 0. That's why we have the center is 0, 1. I have a quick question for you. Suppose I have 2 to the x minus 1. Which x makes this exponent 0? X equal to 1. In this case, the center is not 0 because think about which x makes this whole thing 0. That happens when x equal to 1. So 1 minus 1 is 0, right? So the center is located at 1, 1. Okay, this is just a side note for the future. Let's try one more example. which is exponential decay. The example on the left hand side, or this example here, is the next example that we're going to do. Obviously, the b value is less than 1. That means it's exponential decay function. Let's plug it in 0 first. Anything to power 0 is 1. If you plug it in -1, what's 1/2 to the power of -1? Well, do you believe that 1/2 is same as 2 to the power of -1? And then this -1 is located here. And then you trust that -1 times by -1 makes it positive. So it is a great news, because if you put -1 into the x, it's basically very nice number 2. If you plug -2 into the x, it's basically a very nice number 4, like so. And then this number, if you put 1 into the x, it's just 1/2. If you put 2 into the x, it's just 1/4. And then plot everything on here, then I'm just going to do it quickly, okay? 0, 1, and then the graph is a decaying function. Looks like this. And then you clearly see the horizontal asymptote again. The horizontal asymptote is happening when y equal to 0. So here's the summary. Where is the center in this case? The center is located here, because think about which x makes the whole exponent 0. In this case, x equal to 0 makes this power 0, right? So if we put 0 into the x, the whole y value becomes 1. So this is the introduction to sketching exponential functions. If you understood everything so far with asymptote and center, then you're good. Okay. Okay, everyone. This is the time to tell you how to sketch exponential functions in the most quickest way. When we were talking about this table of values, finding y values and x coordinates for the table of values takes too much time. It takes too much time to sketch exponential functions. So I have invented another way to sketch exponential functions more cleverly. Instead of having A, B, C, D, E method and transform, I call it center and asymptote method. Okay, let's try sketch the exactly same function without using table of values. The first thing you have to find out is look at the b value and then tell me whether it's a growth function or decay function. If you said it's a growth function, then you're correct. If you answered my question about growth or decay, in this case it's a growth function, then in your brain right away imagine the function looks like this, or it looks like this. Okay, do you know why it could go either way? Well, one way is quite obvious. It's going this way, which means the function is growing. Do you understand? It's growing. But hey, Jiwon, I don't understand why it's still growing if it goes downward. Listen carefully. This is growing in the negative direction. Could you please remember? It is growing in the negative direction. This kind of situation happens if you have something like negative sign in front of the function. In module 1, do you remember? This negative sign makes the curve flip. Do you understand? It flips the curve. So that's why even though it's going down, still we treat this as a growing function in the negative direction. Does that make sense? Okay. In this case, what is the center in this case here? The center is the point where it makes the exponent 0. Which x makes the exponent 0 in this case? It is 0. If you put 0 into the function, anything to power 0 is 1. So that's why the center is located at 0, comma 1. Okay? Now, step 3. Step 3, I call it special points. If we have 3 special points, for example, like this, did you see my red dots? 3 special points, and then we know the shape of this, right? Then we can just sketch it like this. So 3 special points is always center in the middle, which is 0 in this case. And then we need to choose the other 2x values. Center is 0, you know that, right? The other 2 values are 1 more than center, which is 1, 1 less than center, which is -1. This is how you find the 3 important x coordinates. Once you figure this out, you can plug these numbers into the function and get the corresponding y values. When you put 0, the y value is 1. When you put 1, the y value is 2. When you put -1, the y value is 1/2. Then you should be so happy to have these 3 special points, which is this, this on the curve. Then you must have asymptote. Asymptote is very important. The asymptote is happening at y equal to 0. Finally, using these 4 steps of information, we have to sketch it. Here's the sketch of the graph. Please follow the reverse order. You must sketch the asymptote first. Sketch the asymptote first, which is located at y equal to 0. That's the asymptote. Now, you're welcome to plug these 3 points. We have -1, 1/2, 0, 1, and then 1, 2. So we have sketched the asymptote. We sketched these 3 points, and then we know what the center is. We know that this function is growth function. Because it's a growth function, you just join the points with this kind of shape, which is growing function like that. Congratulations. This is how you sketch an exponential function without table of values, without like A, B, C, and transform method. This is the quickest way of doing exponential functions sketching. Let's try two more harder than this. We're gonna transform the function like 1 unit right, 1 unit up, or vertical expansion kind of thing. Okay, let it begin. As usual, follow my steps. Step number 1. Is this a growth function or decay function? Look at the b value. The b value is more than 1. That means it is a growth function. So in your brain, you should imagine either it goes this way or it goes this way. Okay, you know why. Step 2. I'll be happy if you tell me the right x coordinate for the center. Think about this, everyone. Which x makes the power, which means exponent, 0? How can we make this thing 0? If x equal to 1, 1 minus 1 makes it 0. So our center must be 1, comma, anything to power 0 is 1. So 1 plus 1 is 2. So our center is no longer at 0, 1 kind of thing. It's now located at 1, 2. We're going to choose 3 special points, namely center in the middle, which means x equal to 1, and then 1 more than center, which is x equal to 2, 1 less than center, which is x equal to 0, and the corresponding y values for each. I have 1.5 because think about it, everyone. We have 0. 2 to the power of 0 minus 1 is 1/2 plus 1. 1/2 plus 1 is same as 1.5. So now that we have three important points, and then it's a growth function, we just need one more piece of information, which is the called asymptote. The asymptote in this case is no longer same as this. It's wrong in this case. The reason is plus 1 means the horizontal asymptote is shifted how many units where. How many units go up, how many units go down. What is the correct answer? The horizontal asymptote is 1 unit go up. So the asymptote is no longer at y equal to 0. Instead, it's located at y equal to 1. And then you know what to do next. You sketch the asymptote first. You must follow the reverse order to sketch the full graph. Y equal to 1 is the horizontal asymptote, and then we plot these 3 points on the graph. We have 0, comma 1.5. We have 1, comma 2, and then we have 2, comma 3. Congratulations, everyone. We have successfully sketched very first transformed exponential function. It's 1 unit right, 1 unit up. We don't have to worry about A, B, C thing anymore. Just find out these answers to these steps, then you'll be fine. Okay, we're almost done with this example. The domain is all real numbers, right? All real numbers means, as an interval notation, it is negative infinity to infinity. That's the interval notation for all real numbers. How about the range? The range is that you cannot touch the asymptote, but the graph goes forever, forever up. So do you have a feeling that all the y values higher than 1? So all the y values greater than 1. It means this is the interval notation for the range. Instead of I write exactly same as the example on the left hand side screen, I change a little bit to make it slightly more harder by putting the negative sign. The purpose of doing this is to give you a variety of different types of examples before homework. Okay, is this a growth function or decay function? If you said it's decay, then you're correct because 2 over 3 is less than 1. Please note, everyone, decay function looks like either this, like decay, or it could go the other way if you apply the reflection. So it's either this or this, but let me tell you the answer. It should look like this. The reason is we have the negative sign. Okay, let's answer step 2. Which x makes this exponent 0? In this case, 1. Okay, now how do we find out the y value? Well, think about this. Anything to power 0 is 1. And then 1 times by negative 2 is negative 2. And negative 2 plus 1 is negative 1. This is the center for this graph. Now we're going to choose 3 special points. I'm going to start with the center in the middle, like this. And then one more than center is 2. And then one less than center is 0. And then we find the corresponding y values. At least we know when x is equal to 1, the y value is negative 1. When x is equal to 2, 2/3 to the power of 1 is 2/3. 2/3 times by negative 2 is negative 4 over 3. Negative 4 over 3 plus 1 is negative 0.333. You can check this with your calculator. If you put 0 into here, then you get 2 over 3 to the power of negative 1. But 2 over 3 to the power of negative 1, you can flip the fraction to make a positive exponent. So it looks like this. If you put 0 into here, then you get this expression so far. But you can flip the fraction using exponent law like this, and then you can cancel the 2, which becomes negative 3 plus 1 becomes negative 2. Yay! So what does this mean? It means our y value is negative 2. Step 4. The asymptote is determined by this number here. We have one translated 1 unit up. Because it's translated 1 unit up, our y is equal to 1 for the asymptote. So altogether, let's sketch the function here. We must follow the reverse order, so the horizontal asymptote first. This is the horizontal asymptote, and then those 3 points are 1 comma negative 1, somewhere here, and then 2 comma negative 0.33, so which is over there. Now you see the shape looks like this. And then finally 0 comma negative 2 is like this. Yay! If you sketch this carefully, this is the decay function in negative direction. We have successfully sketched. So I want to tell you that please don't be afraid if there are too many things going on with the transformation. If you follow my steps, you will have no problem sketching any exponential functions. Lastly, let's find out the domain and range. It goes forever left, forever right, so the domain is all real numbers. As an interval notation, it's negative infinity to infinity. The range is, as you can see from the asymptote, we have all the y values below the asymptote, which means y is less than 1. As an interval notation, it looks like this. Okay, everyone, thank you so much. That's the end of part 2 of the video. In part 3, we're going to do exactly the same thing, except that we're going to use different base. Okay, and then the money problem, compounded annually, semi-annually. But in part 3, we're going to learn something called compounded continuously. See you soon. Part number 3, using the number e. If you haven't seen this number e before, it is time to learn the new number in the world. So first, I'm going to take out a calculator and compute this number e. So e is usually this kind of symbol on your calculator, and if you hit enter, this e is approximately equal to 2.71828 blah blah blah. So this e is not a scary number. It's just a special number symbol for this decimal number here. Okay. So it is about 2.718 blah blah blah. The question is, if we talk about an exponential function, y equals e to the x, what is the base number here? The base is the number underneath the exponent, which is e. Now, since the base b is equal to e, which is approximately equal to 2.718, is it a growth function or is it a decay function? If you answered my question with a growth function, then you're correct. So let's circle this. It is a growth function. Then you should expect to, have the graph looks like this. That's y equals e to the x function. Now, finally, the number e is called the Euler number. Some people call it Euler, but that's wrong. The correct pronunciation of this one is Euler number. Okay, let's move on to the next page. Okay, this is what we're going to do. We're first going to sketch an exponential function involving base e. Let's sketch this. Y equals e to the x plus 1 minus 2. Do you remember what we did in class? We first answered whether this is a growth function or decay function. Growth function. This means you should expect to have this kind of shape. Of course, if your the number in front of the e is negative, you should also expect to have growth function in negative direction as well. However, because our a value here is positive, the graph should go up, forever up. So it's a growth function. Step 2, what is the horizontal asymptote? The answer here is, the reason is you only have to look at the last number. This number tells you about the horizontal asymptote. Special 3 points. I hope you remember how to find this. X equals, x equals, x equals. And then find out the center number first. The center number here is, think about which x makes it 0 on the exponent. Clearly, -1 plus 1 makes this whole thing 0. So the center is -1. And then 1 less than -1 is -2. And then 1 more than -1 is 0. And then let's find out corresponding y values. You put -1 here, then anything to power 0 is 1. So 1 subtract 2 is -1. If you plug in 0 into the function, e to the power of 1 minus 2 is, what is it? It is 0.718. So we should put 0.718. How about the other one? You have to do. It is -1.63. Did you notice that I put -1 here? Because if you plug -2 into the function, we get -2 plus 1, which is e to the power of -1. This whole thing is -1. That's why I put it here, e to the -1 minus 2, which is this y value. Now, feel free to sketch with the horizontal asymptote first, and then plot the 3 points. Congratulations, this is the end of the example. Let's do one more sketch problem. This time, I will give you a little bit more difficult one, which is negative exponent. Hot tip. E to the power of negative x is not equal to 1 over e to the power of x. You can change the negative exponent as a positive exponent like this. That's the one of the exponent rule. So the question is, what is e to the negative 0.5x turns into? It turns into 1 over e to the power of 0.5x. But more precisely speaking, this is equal to 1 over e to the power of 0.5x. Okay, so now that we have this expression, let's rewrite the function as follows. Y equals. Next, I have one question for you. Did you notice that we have base 1 over e? Do you think this function is a growth function or decay function? If you said it's a decay function, then you're correct. The reason is this. 1 over e is actually less than 1. This decimal number is less than 1. That's why this is a decay function. Now, everything else is the same. Horizontal asymptote is y equal to 0. 3 special points that we need to choose. Think about which x here makes the exponent 0. So the center point must be 0. And then 1 less than 0 is -1. 1 more than 0 is 1. And then the corresponding y values are, this is much easier. You put 0 into the exponent. Anything to power 0 is 1. So 1 times by 4 is 4. And if you plug 1 into the x, then the y value is 2.426. And then the y value is 6.59. Now we are ready to sketch this function. Sketch the horizontal asymptote first. And then plot those 3 points. And then feel free to plot them. Congratulations. This is how you sketch the function 4 times e to the negative 0.5x. Thank you, and we're moving on to more real-life problems. All right, this is the last part of today's lesson, and we're going to study more real-life word problems, such as money and population again. Money problem, we already know annually, semi-annually, and so on, then you can probably choose n. The question is this: what if it's compounded continuously? Whenever you hear the word continuously, this n is actually infinity. Don't be scared. Okay, everyone, don't be scared. Um, Infinity is not a number. It's just the compounding period is just infinite. In other words, this n is infinite. Here, n is infinite. You do not know calculus yet, so I'm just gonna tell you the formula whenever n is infinity. In other words, whenever compounded continuously, the formula that you have to use is a equals p times e to the power of some rate r t. Now, p is the initial amount, a is the final, r is the growth rate, and then t is the number of time. And that's the formula that I was trying to talk about. Okay, let's try some examples. The population growth problem is very similar to that of the previous one. It looks like P, the final amount, equals initial population times e to the RT. Okay, this example is pretty straightforward. They gave you the initial population and then the constant growth rate, 0.22. Estimate, oh, there's a typo. Estimate the population after 4 hours. So you just have to do this. Using our calculator, this shows that our final population of this bacteria is 168.76. So about 169 number of bacteria. Last example for today. You deposit this much of initial amount. So this is P equals 500, and then 3% is the annual interest rate. R is equal to 0.03. Compounded continuously. That means you have to use this formula. Okay. And then we know all the pieces of information. Here, 2 years is the time, and then 0.03 is the annual interest rate, and then 500 is the P. That's why I put all the numbers here and use your calculator to get $530.92. Thank you, everyone. That's the end of exponential functions. I'll come back with logarithms. See you soon.